Let's say you've been asked a question about a certain video game. The map is on the screen. Here are the rules of the game. You're trying to rescue Princess Peach. If you fall in the fire pit, you die, and if you run into a wall, you stay where you are. Here is the question. How would you program an AI to do this? Now, if you were Chris Watkins in 1988, you might try to use the memory of the computer to your advantage. This is done through using a large table called the Q table. In this table, we can store the expected reward that comes from every possible state and action. A state is basically the environment at a certain time. In our game, we can number the squares from 1 to the end, and then our state would just be where Mario is. An action is just a move that we can make. In this scenario, we can only move left, right, up, and down. So our Q table would look something like this. Now, the number we store in these squares right here are called Q values. These values represent the reward we expect for doing that move, or doing a series of moves after that. Now, you might ask, what's with the Q? Well, first of all, also, it stands for quality, because that's what we are really trying to do here, is determine the quality or usefulness of every action in every state. I should mention that, even though this is not a problem with our example, some games have a continuous movement system, and these can be difficult to work with since the coordinates can range down to almost 8 decimal places. I mean, just imagine filling out a table for that many values. Our computer would probably crash or heat to the boiling point before we even got a fraction of the way done. So we need to group some of these values together. This is called bucketing. Here's how it works. We take the ugly 8-digit decimals and put them in buckets. For example, we could put 3.141592 in the bucket of numbers ranging from 3.1 to 3.2. This tremendously reduces the amount of data. But since our example is discrete, basically meaning that it's not continuous, we don't have to do any of that. Now, all we have to do is create an equation to determine these Q values. Try to think about this for a second. Well, a simple idea is to just set the Q value as the reward we receive from doing the action. So our equation will look like this. Here, S stands for state, A stands for action, and R stands for reward. Now, let's see what this would do to the Q values in our grid. I should mention that the values shown in the grid are going to be the maximum Q values for that grid. In other words, these values are going to represent the expected reward for the best action. Okay, so let's say that after tons and tons of exploring, we have finally saved Princess. We have fallen into the fire at least once. Then, our Q value for the square right before saving Princess Peach would be 1. The values going into the fire pits are -1, but since these are not the maximum, they won't be shown. Now, let's see the rest of the Q values. Dang it! So, what did our program do wrong? Well, our program doesn't think long term. It only thinks of the reward it receives after one action. Since our program doesn't have any long-term thinking, let's add some. So how will we do this? We can think of state after the state that we are in. Let's call the state that we want to go into S prime, and the possible actions that we could take in that state A. We want to find the maximum Q value for all the possible actions, or A's, that there are. We can symbolize that like this. We can add to that equation, getting us this. Now, let's try again. Wait. What about the final state? Since the final state has no state after it, our equation doesn't work. But it turns out we can just have the final state, denoted S sub F, equal to the reward R. Now we can try again. We have saved Princess Peach, so that Q value is 1. Likewise, we have also gone into the fire pit, so those Q values are -1. Now let's run through Let's run through the program again. We get to the second to last square, where the max Q value afterwards equals 1. Therefore, this Q value is set to 1. Similarly, we run the program again, getting this square to be 1 as well. Similarly, we run the program again, getting this square to be 1 as well. Oh dear. Now, our program doesn't care about the number of steps it takes to get to the solution. So what is our solution? Greek letters. Actually, our solution lies denoted with a gamma, or a Greek G. The discount factor basically determines our program's short-term and long-term thinking. If we have a low discount factor, the program will emphasize short-term thinking over long-term thinking. But if we have a discount factor near 1, then we see the program values long-term thinking more than short-term thinking. If the discount factor is above 1, then things start to break, since it values the goal more the longer it takes to get there. So we insert the discount factor in there, and we try it again. Since we want our program to value long-term thinking, let's set our discount factor to 0.95. Now we have saved Peach, so the value of the state right before the goal is 1. Then the Q values of the squares leading up to that equals 0.95 times 1, or 0.9. Then the squares leading up to that equals 0.95 times 0.95, which equals about 0.9. Here are the rest of the maximum Q values for each square. And voila, we have officially developed a Q-Learning AI. But wait, you might say, this doesn't relate to real games at all. Real games have RNG. For those of you who don't know, RNG stands for Random Number Generator. It's the random chance that lies in almost every game. So let's simulate this. Let's say that Mario has been working on his physics PhD, and he is so sleep that he has an 80% chance of going where he wants to go, a 10% chance of going left, and a 10% chance of going right. Now, if we try to apply our algorithm here, we will end up with highly fluctuating values around the fire pit, since sometimes we will accidentally fall in. Therefore, we probably want to somehow include the old value and add this up with our expression for the new Q value to help stabilize this. How can we do this? Yes, we're doing this again. The Greek letter alpha is used to denote the learning rate. We call it this because it determines how fast the program learns. The lower the learning rate, the slower to get to the values, but the more accurate those values are. So how can we implement this? We can use the concept of weighted averages. Let's multiply the old Q value by 1 minus A and multiply our expression for the Q value by A, yielding this equation. And now we have officially developed the equation used for Q-learning. This type of equation is called a Bellman equation, which is an equation that optimizes a program recursively. And we are done.